Good morning, good day, good evening, good night. I don't even know when you're watching this video. Welcome to Unit 4 videos for asynchronous learning or just to re-listen to stuff that I say. We're going to be going through this Unit 4 unit that was redundant, Unit 4, which are going to be applications of derivatives. So now that we know what the derivative is and we know what it means and we know how to algebraically find the derivative with the 872 rules we learned last unit, now we're actually going to put those rules into practice and learn some applications of when and how and why we use the derivative. So we're going to get started today with the day one notes, introducing a topic called related rates. And we're going to start this topic today and then finish this topic next class or next time you listen to me, whenever that may be. But we're going to go through and kind of talk. The objectives are: what is a related rates? What do I mean when I say related rates? How do I recognize situations that are dealing with related rates? And then how do I solve problems that deal with related rates? Okay, so we're going to kind of go through and talk about some fundamental understandings, and then we'll do some practice, some strategies on how to solve these types of problems. And then we're going to do a few examples of a related rate situation and how we solve it. I think we're going to end up doing 5 examples, okay? So to get us started, we're going to just start with relationships in mathematics. And sometimes we have relationships in mathematics that are defined by several variables. For instance, let's say we have a relationship like this: x squared plus y squared equals z squared. This is an equation that relates x, y, and z together. Okay, now all 3 of these are variables in this situation. And if you recognize this, this is a little like right triangle theorem. X and y are probably legs of a right triangle. Z is the hypotenuse of the right triangle. And this is the relationship that exists between those sides of a right triangle. Okay, in a situation like this, again, x, y, and z are different variables. They are not going to be constants in this situation. So this is an example of an equation that relates these variables together. Now, when we are talking about how this situation may change, this is when we're talking about the rate or the derivative. Okay, so if, let's say, I wanted to find the derivative with respect to x. Now that's telling me in this situation that x is the independent variable and that y and z are going to be dependent on what x is. In other words, y and z are functions of x, since we're taking a rate with respect to x, which means x is the independent variable and y and z are the dependent variables. So now, if I wanted to find the derivative of this, because this equation is implicitly defined like we talked about last unit, I'm just going to take the derivative from left to right. Now I have to be careful here because some of these variables are the independent variable, aka x, and some of them are functions of x. So if I take the derivative from left to right, I would take the derivative of x squared. Now, x is the independent variable, so its derivative would just be 2x. Now, if I take the derivative of y squared here, we have to remember that y is not just an independent variable. Y is dependent. It is a function. This is a function being squared. I'm going to have to use chain rule when I take the derivative. So it ended up being 2y, derivative of the outside, times dy dx, which is the derivative of the inside. The inside in this case is the y. Okay, so the outside was the square, the inside was the function y. So I took the power rule for 2, brought it down, kept the y the same, and then times it by the derivative of y. And since y is a function, its derivative is another function we call dy dx. Now the same thing with z here. This is z squared. This is a chain rule, so I'm going to bring the 2 down, make it z to the first times the derivative of the inside. Now in this situation, I'm treating z as a function of x, which means if z is a function, its derivative is another function I would call dz dx. Now if you look at the result here, I end up with a relationship, aka an equation, that relates x, y, z, and the rates of y and the rates of z together. This is what we call a related rates equation. It's just an equation, okay, that relates rates together. Now, let's say I wanted to take this same relationship, okay, that I started with, but now I want to take the derivative with respect to time. Now, notice that there is no t in my equation, which tells me, okay, that each of these variables is a function of time, kind of like in a parametric situation. So when I take the derivative here, all of these variables are considered functions of time. And so when I take the derivative of each piece, since it's implicit, I'm going to end up using chain rule for every single part. It's going to be 2x to the first times the derivative of x, which if x is a function of time, its derivative would be dx dt. The rate of x with respect to time. I almost wrote dx dx. Okay. I'm just going to erase that real fast. Plus, okay, 2y times the derivative of y with respect to t would be dy dt. The rate of y with respect to time equals 2z times dz dt. Okay, now the whole purpose of taking the derivative here, other than just for practice, is that if you look, we end up with an equation, which is a relationship in mathematics between variables, and this equation relates these rates together. So now what I have is an expression or an equation, a relationship between rates. That, my darlings, is a related rates situation. Anytime we have a situation where we have things that are moving and changing that are mainly dealing with time, where time is the independent variable in the situation, we would solve these rates problems. And these rates problems are what we call related rates. So I would get an equation that relates the variables together, and then I would get an equation that relates the rates together, and then I'm going to use that equation to solve different situational problems, okay? Now, unfortunately, there is not like one-stop shop as to how these problems are going to be solved. You'll recognize them because everything is going to deal with time. All dependent on time. So in related rate situations, you're going to read a situation and you're going to go ding, 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 ding. This is related rates because time is the factor, all dependent on time. There you go. Okay. Just so you guys know, it is election day when I am filming this, for better or for worse. When you listen to this, who knows how you're feeling? Okay. But that's when I'm filming this. So we're going to be talking about how do we solve related rates problems. Well, step one, when you're doing these, okay, some strategies that you're going to use. Okay, let me jump ahead of myself. So again, related rates are situations with moving parts, okay, all dependent on time. Okay. For example, if I asked you, I'm blowing up a balloon. As I blow the balloon up, what's changing about the balloon? Well, you could say radius is changing, the surface area is changing, the volume is changing, the diameter is changing, the pressure is changing, the elasticity is changing. In that one situation, as time goes on, there are a lot of different factors that are changing in that situation, meaning there's going to be a lot of rates. There's a rate that the volume is changing. There's a rate that the radius is changing. There's a rate that the elasticity is changing. Like all of these things, because they are changing, will have rates. Our goal then is one, I want to be able to figure out one of the rates, and I'm going to do that by writing an equation that relates the rates together. Okay, so how are we going to do this? Strategies and tips to solving related rates. 1, draw a picture, okay? These are going to be moving things. We're going to be talking about how they change or what their rates are. Draw a diagram. Label that diagram with things that are relative to the problem. Now, there are 2 types of parts in a situation that is related rates. Things that are moving or changing that you're going to label with variables, okay? Things that are not changing, that are constant. Those constants, you can put down the number that is, but do not put numbers on your diagram unless they represent things that are constant, okay? Now, you're going to look for a relationship between the variables. Your goal is to get a relationship between the rates, but that's almost impossible to think about. But what you can do is look for a relationship among the variables, some sort of geometric relationship or physics relationship. There's got to be something that relates those parts together. Once you get a relationship among the variables, then you can take the derivative with respect to time implicitly, and that will give you a relationship for the rates. Okay, love and cherish the chain rule. All of these things are going to be functions of time, and so chain rule, chain rule, chain rule. Be careful with your notation. We're going to avoid prime notation here. Prime notation gives no respect to time, which is not going to be usually a part of this. Okay, so be careful. You try to use Larry notation or Leibniz notation, the slope notation, like dx, dt, dy, dz, like with those types of slope notation, as opposed to the prime notation. Okay, so step 1 is to figure out what's going on. Step 2 is to write a relationship, write an equation for the variables. Step 3 is to take the derivative with respect to time. That's going to give us a related rates equation. Once you have that related rates equation, then all you're doing is plugging in the values that are known and solving it. And then the final thing you want to do is interpret your solution, answer the actual question with units. So we're going to practice some of these. And I'm going to kind of show you how I set them up and how I kind of do them. And then, we kind of go from there. So let's stick with our balloon. I think that's supposed to be a balloon. A spherical balloon is inflated with helium at the rate of 100 pi feet cubed per minute. So now this is a situation, like if I was reading this word problem, I see that I have an object. I see that it has a rate, and that rate has a time factor in it. This is my ding, ding, ding. This is a related rate situation. Related rates. I notice it. Okay. I want to know how fast is the balloon's radius increasing at the instant when the radius is 5. Okay, so in a related rates situation, you'll recognize it because we're going to have some sort of object changing or something's in motion, and we're trying to figure out some rates. They're going to give us rates, and we're going to find other rates, but that's like the last step. All of these things are changing situations. And what we're going to do is with this situation, we're going to freeze it for 1 instant and figure out at that moment what are all the rates and information about the problem. Okay, so to set this up, I like to do like my given and my find. Kind of like your given and prove back in geometry. It's like what I'm given, right? And what I'm trying to find. So if I draw my picture here, here's my balloon. Okay, I have like a sphere, so I should probably make it look like a sphere as opposed to the letter O. Okay, now if I think about this, what's happening is this balloon is being inflated. So I like to tell myself, okay, what's happening here? The balloon is being blown up. So I know it's getting bigger. It's not staying the same size. Now, if I think about what's changing in here, we have a radius of this balloon. And because that radius is not staying constant but changing, I'm going to label that radius R. Okay. Now, the given information are the things that they tell us to begin with. Well, they tell us that a spherical balloon is inflated with helium at a rate of 100 pi feet cubed per minute. So I need to look at this constant that they give us, and I have to identify what that constant means for this situation. If it is 100 pi feet cubed per minute, I'm trying to think of what that is. Well, I know it's a rate, so it has to be a derivative value. I have to figure out what it's the rate of. And since it's talking about inflation, and if I look at the units here, I see that the units are feet cubed. That tells me this is the rate of the volume. Now, if I had to give that volume a name, like I usually will call volume V, right? Maybe I'll just do a little V out here. So the rate of volume with respect to time, because that's what it says, would be dV dt. So my dV dt here is 100 pi. Now I need to figure out, based off this situation, if this is a positive constant rate or a negative constant rate. And because it's being inflated, I know it's a positive constant rate. I leave the units off when I write down the numbers. I just like to kind of see what's happening. The other thing I do is like to draw like what's happening there. Now it's always going to ask me to find something at an instant. Okay. So I'm going to do like a find something when something. So there has to be a time and there has to be something I'm looking for. So if I look at this problem, it says, how fast is the balloon's radius increasing? Okay, well, the radius here I know is changing. So I'm not trying to find what the radius is. I'm actually looking for how fast it's increasing, which means I'm looking for the rate of the radius. So in all of these problems, you're going to be looking for a rate of something, which means we're going to be looking for a derivative value or a rate value. Okay, so I'm going to be trying to find dr dt, and that's what I'm going to call the rate of the radius. Now, the moment that I'm doing this is when r is 5, when the radius is 5. And that's kind of how I set the problem up, is I like draw the picture, I see what's happening there, and then I figure out what information do I know, what I call the given or the secondary information, and what information am I trying to find and at what instant, because all of this is instantaneous. Now, step 2 is to look for a relationship among the variables in here. I'm not going to pay attention to these rates. My goal is to find an equation that relates these rates together, but I have to start with just the variables themselves. And the only variables I have in here are r, which is my radius, and v, which is my volume. So I'm going to think to myself, oh man, okay, I have a spherical balloon. Is there a relationship between the volume of a balloon and the radius of the balloon? Yes, it's a geometric formula. The volume of a sphere is 4/3 pi r cubed. Now you're like, oh my God, Ms. Bowman, I do not remember the volume of a sphere for you. You'll be given sphere and you'll be given cone, but you should know how to find like the volume of a box, okay? So that's kind of step 2. Look for the relationship among just the variables. Okay, now, once you do that, here's where the calculus part comes in. We have a relationship between variables. What we want is a relationship between their rates. So what I'm going to do is take the derivative with respect to time, since time is the factor in this problem. So V is volume. Its derivative would be a function we call dV dt. I'm not going to say V prime here because I want to give respect to the time factor, which is not a variable in this situation. So the only way I can notate that I did this with respect to time is by writing it as dV dt as opposed to V prime. Now, when I look at the right side, I'm going to take the derivative implicitly over here. 4/3 pi is just a coefficient. So that kind of comes down. It's the constant multiple rule. Times, now I'm going to take the derivative of r cubed. I just have to remember that in this situation, the radius is a function of time. So when I take the derivative of r cubed, I'm going to have to use chain rule here because r is a function and that function is being cubed. So I'm going to bring the 3 down and make it r squared times the derivative of the inside, which if r is a function of time, its derivative would be dr dt. Okay, so in this relationship, we're not treating volume as a function of radius. We're treating volume and radiuses radii as functions of time. Okay, so that's why I'm taking the derivative with respect to time. Now, if you look at what we got here, I'm just going to clean this little guy up a little bit. I have an equation. Those 3's would cancel. Okay, I have an equation, or in mathematics, a relationship that relates the rates of volume and the rates of radii together. So the dv dt and the dr dt are in an equation. This is what we call the related rates equation. Now we are going to solve this related rates, I can't talk, related rates equation for this specific instant. So now that we came up with an equation for the variables. Now we have an equation for their rates. Now I'm going to go to what I'm trying to find when. So what I'm looking for is dr dt. So here's what I'm going to do. I'm going to figure out all the information that goes with this problem at this moment, and I'm going to plug in all that information to make sure I have everything I need. So at this moment that I'm freezing this balloon at this instant, I know the radius is 5. So I'm going to plug in 5 for the radius. Also, in this situation, dv dt is a constant, meaning it's going to be the same the whole time. So I'm going to plug that rate in for the volume, and that's going to allow me to find the rate for the radius. So I end up getting 100 pi equals 100 pi times dr dt. So if I solve for dr dt, I end up getting 1. And now I just have to think about my units. The radius of the unit was measured in feet. So the rate of the radius should be feet per minute, because that was the time unit. And all we wanted to do was find the rate of the radius. We did that, and so the problem is done. So what does this mean? It means the radius is increasing at a rate of 1 foot per minute when the radius is 5 feet. So when the radius is 5 feet, we know it's increasing at a rate of 1 foot per minute. And that is related rates. So what we're going to do now is just practice 4 more related rates questions together. Okay, so here we go. Eric and Anthony take a break from racing each other in sprints to paint a house. Anthony is holding the base of a 15-foot ladder, and Eric is halfway up house on the ladder, painting the house. The bottom of the ladder is initially 12 feet away from the wall and is being pushed towards the wall by Anthony in order to get Eric higher up on the house at a rate of 1/4 feet per second. How fast is the ladder moving up the wall 12 seconds after he starts pushing? So I read this, I'm like, oh my God, there's a lot of words. It is a situation. That situation has changing things, and I'm looking for how fast is the ladder moving up the wall? 12 seconds. So I can recognize this as a related rates situation. 1, because they're asking me to find a rate, and 2, the rates in the problems have to deal with time. So those are your context clues. Now I need to draw a picture of what's happening here. So I know I have the side of this house, and I have a ladder here, and someone is halfway up the ladder painting the house with their Stretch Armstrong arms. And then someone is at the bottom of the ladder pushing the ladder in. Okay, so if I think about this situation, I know that Anthony is pushing the ladder towards the house, and that means Eric is going to be moving up on the house. And that's kind of the situation that I have. Now, geometrically speaking, what have I created? Well, I've created a little right triangle. So what I want to do in this right triangle is I kind of want to think, okay, what's changing and what's staying the same, and what information do I have? So if we go to our given, let's look at what we need, let's look at what we were told in the problem. Okay, we know the ladder itself is 15 feet. I'm actually going to label the ladder 15 feet because the ladder itself isn't changing. It's just going to be 15 feet no matter what. The only thing that's changing is the distance here from the bottom and the distance the ladder is up on the wall. So when I label my picture, I'm going to call this distance B and this distance H. Why? Base and height. Otherwise, I don't know why else I would do it. Okay. The bottom of the ladder is initially 12 feet away. So we'll say the base of the ladder initially is 12 feet away. and is being pushed towards the wall at a rate of, now this is the rate of the base, so I'm going to call that rate dB dt is equal to 1/4. Now I have to imagine here, is the base increasing or decreasing? It's never going to tell you what sign it is. You have to assign it using logic. Okay, so if I push that base in, this b, this distance is decreasing, which means I should have a negative rate. Now let's think about my find when. Okay. So I'm trying to find how fast this ladder is moving up the wall. So that's the rate of the height of the ladder when time is 12. Okay. So that's the setup. That's like part one of the solving these problems, is setting these problems up. Now what we're going to do is we have to find a relationship or look for a relationship that relates just the variables. I'm not talking about the derivatives or the rates. I'm not thinking about rates at all. I'm thinking about if I just gave you this picture and asked you to relate those things together, how would you do that? Well, if I'm looking at this picture, I notice that I have a right triangle and that I have sides of a right triangle. So I'm going to use the right triangle theorem and say that h squared plus b squared has to equal 15 squared. Now notice in my equation, okay, when I started this equation, I have b a variable, h a variable, and 15 a constant. Okay, 15 represents the ladder. I only put 15 in there to start with because 15 isn't changing. If the ladder was changing size, I would have to use a variable for the ladder. But because the ladder is constant, I can go ahead and put that constant in. So here's my equation. Now the next step is to take the derivative with respect to time. So again, these variables are functions of time. We're knowing, loving the chain rule. I'm going to bring down the 2. It'd be 2h times the derivative of h, which is dh dt. This is going to be 2b times dB dt. And 15 squared, that's a constant. Its derivative is 0. So that's kind of why I put constants in there. If you would have put like L squared, it wouldn't be wrong. You would just have to know from the situation that dL dt is 0. Okay. Now, that's step 3. So step 1, draw a picture. Step 2, write an equation. Step 3, find the derivative. Because now I have an equation, a relationship between the rates of this situation. Now I have to look at my moment and plug in information from this moment. So at this instant, let's think about what's happening. I'm looking for dH dt. I always put a box around who I'm trying to find, and I'm going to ask myself, do I have all the information gained? Okay. In order to figure out this rate, I need to know all these other variables at this moment. dB dt is a constant, so I know that one because it's negative 1/4. So I'll be able to plug that in. Now, B and H are changing in this situation, but I have frozen this. So I need to figure out, do I know what the height is and the base is at this time that what we want me to do? And I don't think I do. I do know that it's been 12 seconds. So what I need to do then is I need to figure out in 12 seconds, what would be the length of the base and the height of this right triangle? Well, we got to think through this, okay? I know 12 seconds have gone on, and I know the base started at 12. So at time 0, it's 12, but it's moving in. So it's not 12 the whole time. It's only 12 at the start. So I need to figure out where it's at 12 seconds later. Oh, but I do know that the rate is 1/4 of a foot per second. So if I know 12 seconds have gone by, I'm just going to do like 1/4 times 12 seconds and then do 12 minus that to get my base. And that's going to give me a base of 9. So at this moment, the base of the triangle is 9. I like to call this my aside. You guys know I like the word aside. It's just like all the stuff that I'm figuring out at this moment that I'm going to need to plug into my equation. Now I would use the right triangle theorem to find the missing side. I do see that it's 15, 9, which means it's a triple, 9, 12, 15. Okay, so this is when t equals 12, what my triangle would look like. And so I'm going to use the frozen triangle at time 12, and I'm going to plug in that information here. So I got 2 times my height of 12 times dH dt, which is who I want, plus 2 times my base of 9 times my rate, which is negative 1/4, and that's going to equal 0. That gives me 24 dH dt minus, let's see, 18 divided by 4 is negative 4.5. Okay, equals 0. And so if I solve that equation, I get that the height is 4.5 over 24. And then I have to think about the units. Well, height itself is going to be measured in feet. The time is measured in seconds, so it'd be feet per second. Now, I always like to make sure that that makes sense situationally. So if I look at this, because the ladder is being pushed in at the bottom, I do know that it's going to go higher up on the house. So the height of the ladder should be increasing against the house. I did end up getting a positive rate, so that's a quick check to make sure it works. Okay, let's try another one. Charlene has become a television reporter and is doing a story on race cars. She goes to a race and videotapes it from a stand 132 feet from a track. She follows a car that is moving 180 miles per hour at 264 feet per second. How fast will her camera angle be changing when the car is right in front of her? Okay, so I want to figure out like what's happening in this situation. So I'm going to assume that she's in front of the straight part of the track. So I'm going to do like a bird's eye view of this situation. Bird's eye view. So here's Charlene over here with her ponytail and her camera. Okay, that's her camera. I'm a really good drawer, guys, just so you know. Okay, and she's filming it. And then there's this car. I'm going to try to draw this car. It's from the air. So here's the car. Here's the spoiler. Here's the windows. Yeah, it totally looks like a car. And the car is moving this way. Okay, so I have that. Now, I do know that she's staying put and that her distance from the track is 132 feet. So I'm going to go ahead and label that as 132. There is the distance that she is from the car and the distance the car is from her line of sight. It's talking about an angle. So I'm going to make sure I label that angle theta. And then here, I'm going to label this C for car. That is changing. Now, if you also want to label this, we could call this like X. That's also changing, okay? I always draw the picture and label the picture. Remember, anything that is changing, okay, you are going to be writing with variables. Anything that is constant, you can label with the number. Even though it like gave us these other numbers, I'm not labeling that on my picture, okay? I also like to indicate direction by drawing these little arrows. That just kind of helps me figure out, are the rates going to be positive or negative? So I can see if the car starts up top, it's going to end up being like a negative rate, at least for a while until it's right in front of her. And then it's going to end up growing again because it will pass that line of sight. All right, now let's see what's given. The car is moving at 100 miles per hour, 264 feet per second. So the rate of the car, which I'm going to call dc dt, is 264. Now, if I think about this, okay, 264, the car's distance from her line of sight is decreasing at first. So I'm going to put it as a negative rate just because the distance is decreasing. Okay, and then let's see. We're trying to find the rate of her angle. So we're trying to find the rate of the angle when the car is right in front of her. So I can say when C equals 0, or I can see when theta equals 0. I can put it in terms of the car or in terms of the angle. It doesn't matter. But that's kind of the situation we have here. So I drew a picture. I wrote down all my information. Now my goal is to come up with the equation that relates these variables together. Now, I do have a right triangle and I have an angle, which gives me a context clue that I'm going to be having to use one of the three trig relationships, sine, cosine, or tangent. If I can involve the constant, guys, my life would be a lot easier. So I do notice that we have this 132, and then I have the choice between using X or using C. So if I look at the information, I know the rate of C. I'm going to use C. So if I use opposite and adjacent, that's going to be tangent. So my equation would be that the tangent of theta is equal to c over 132. Okay, now you could also say that theta is equal to the inverse tan of c over 132. Either one would be fine to write. Okay, one of them is explicitly defined for theta. One of them is implicitly defined. It doesn't really make a difference. I just try to avoid inverse trig derivatives as much as possible. So I'm going to stick with the first equation and I am going to find the derivative. So I'll kind of do both of them side by side, I guess, so that you can see them and kind of see how to do that. I'm just going to move it over. Yeah, there we go. Give myself some room. Okay, so if I do it this first way, I'm going to take the derivative implicitly. Now remember, guys, in this problem, theta is not a independent variable. Theta is actually being considered a function of time. So when I take the derivative, I have to use chain rule. The derivative of tangent is secant squared theta times the derivative of theta, which would be d theta dt. Now the right side is kind of nice because we have c over 132. Now you can use low d high here, but I know dividing by 132 is the same as multiplying by the reciprocal. That's just a constant multiple, guys. So I'm going to pull the 1 over 132 off, and then the derivative of c is dc dt. And that would be the equation that relates the rates together. Okay, in this one, I would get d theta dt equals 1 over c over 132 squared plus 1 times the derivative of that, which would be 132 times dc dt. Okay, so either way we go, we're going to get the same answer. Now, from here, I'm going to look at this moment. So here's my aside. At this moment, we know that c is 0. Or you can think this is 0 radians. Okay, because the car is right in front of her. Now I know dc dt at this moment is negative 264, so I'm going to put that in. And then secant of theta, well, that's just going to be like secant squared of 0 because that's my angle. Or I could be like hypotenuse over adjacent if I was doing like a normal triangle. But since I know it's 0, I would have that. So I get secant squared of 0. Now I'm going to evaluate secant squared of theta, guys. And this is just negative 2. Secant of 0 is just the reciprocal of whatever cosine of 0 is. So if I think about it, this is the same thing as 1 over cosine squared 0. Okay, cosine of 0 is 1. 1 squared is 1. It's just the reciprocal. So I end up getting that d theta dt is equal to negative 2. Now my units here, we are talking about an angle. Theta would be radians. The time unit is seconds, so it would be negative 2 radians per second. Now, if I did it the other way, I would just plug in 0 for c. And I would plug in my negative 264 for dc dt. I end up getting 1 times 1 over 132 times negative 264. And I get d theta dt equals negative 2. So I get the same thing either way. It just kind of depends on what you're comfortable with. Okay, but that would be that problem. So 2 different types of right triangle problems. We have a right triangle problem with the sides and a right triangle problem with the answers. Now, a lot of times, guys, I will tell you that generally the relationship is going to be geometry, and a lot of times it's going to be a right triangle. Okay. Daniel in his police cruiser is approaching an intersection from the north and is chasing a speeding car that has turned the corner and is moving straight east. When the cruiser is 0.8 miles north of the intersection, the car is 0.6 miles east. Daniel determines with a radar that the distance between them is increasing at 15 miles per hour. If the cruiser is moving at 60 miles per hour at the instant of measurement, what is the speed of the car? Okay, so I'm going to draw this situation. I have an intersection. Again, I'm doing a bird's eye view. I have Daniel in his police car. So we have a police car here. Here's the little thing, traveling south. A speeding race car. Let's see if I can draw a speeding race car. That looks like a speeding race car. It has turned and is traveling east. Now, if I think about this, this is another right triangle problem. The car here, Daniel's car, his distance is, he's going closer to the intersection. I'm going to label that side Y. Even though it gives me some numbers in here like 0.8 and 0.6, I'm going to label my picture with Y because it is a changing distance. I'm going to label the car as X. Doesn't really matter. I could have called it C. And then the distance between them is also changing. I'm going to call that Z. Okay, so in this case, none of these three sides are constants. Unlike the ladder problem where the ladder was a constant, in this situation, all three sides would be changing depending on the time. Okay, so let's talk about our find when and our givens. Okay, if the cruiser is moving at 60 miles per hour, so the cruiser is Daniel's car, I'm going to give it that dy dt is 60. Now I do need to think about the sign here. Because y is moving down, that would be a decreasing distance. We're going to call it negative 60. What we're trying to find is the speed of the car, which would be dx dt. So we're trying to find dx dt when dy dt is 60. Actually, that's just when he's going. Let's figure out the instant. When there it is. When the cruiser is 0.8 miles north. So we're going to say when y equals 0.8 and the car is 6 miles east. So x equals 0.6. Okay. Now the only other thing is I know the distance between them is increasing at 15. That's going to be dz dt. So dz dt here is 15. And it says it's increasing, which tells me it's positive. Okay, so I got my situation. I'm going to figure out the relationship, which is probably formerly known as Pythag, the right triangle theorem. Okay, now that I have the relationship, I'm going to take the derivative. Again, no numbers plugged in. Nothing is constant in this situation. I don't plug anything in until after I do the differentiation. So 2x dx dt, chain rule. 2y dy dt, chain rule, equals 2z dz dt, chain rule. Now at this moment, let's figure out where we are at. So at this moment, we know that this distance is 0.8 and this distance is 0.6, which means I could figure out at this moment, this distance would be 1.0 because it's a 6, 8, 10 triple, or I could use the right triangle theorem to figure it out. I'm looking for dx dt. I know everything else, and I have x, y, and z based off my moment picture. So 2 times 0.6 dx dt plus 2 times 0.8 times negative 60, because remember that distance was decreasing, equals 2 times 1 times 15. And now I'm going to solve this. 1.2 dx dt minus 96 equals 30. Dx dt would equal 30 plus 96, which is 126 over 1.2, which is roughly 105 miles per hour. It makes sense that it's positive because the distance from the intersection is increasing. So the car was traveling east at 105 miles per hour, which seems pretty reasonable for the situation, although super, super fast. Okay, let's try one more. Brisa has been transformed by her evil calculus teacher into a small particle that moves along the function y equals x squared plus 1. Find the rate of the change of the distance between the origin and Brisa if dx dt equals 2 centimeters per second and she's currently at x equals 1. Okay, so let's draw a picture. We have a function y equals x squared plus 1 that I've transformed Brisa on. Now she's at some point, but her point is changing because she's just moving along, trapped infinitely, and she's just going to travel along there forever and ever. And we're trying to find the distance from her and the origin. Okay. It does give me that dx dt is 2. And she's currently at x equals 1. So we're trying to find, okay, the rate of change of the distance between the origin and Brisa. So let's call this B for Brisa, and we're trying to find dB dt when x is 1. And this is what we have, y equals x squared plus 1. Okay, so let's figure out what we need here to do. Well, we need the distance formula. They kind of told us the equation to use. So the distance formula, I hate the distance formula. B equals the square root. Now, what is nice is that I have x minus 0, because it's the origin, plus y minus 0. Okay. And so B would equal the square root of x squared plus y squared. Now I need to find dB dt. So I'm going to use chain rule here. So I'm going to bring down the 1/2. Then it's going to be x squared plus y squared to the negative 1/2 times the derivative of what's inside. So it's going to be 2x times dx dt plus 2y times dy dt. And there's my function. So now I'm going to clean this up, and I get 2x dx dt plus 2y dy dt over 2 square root of x squared plus y squared equals dB dt. Okay. Now, I'm looking for dB dt, which is nice, because all I'm going to have to do is plug in everything in, and it's already solved for it. The question then is, what am I going to do with this information over here? Do I have everything that I need? Okay, well, let's see. They tell me at this moment. So at this moment, let's think about what's happening. I'm at the point 1. So I do have the x coordinate. I also know dx dt, which is 2. So I have dx dt and I have x, but I don't have y. Ooh, but they do give me a function. So I know if I plug in 1 to the function, I would get the point 2. So I know the point 2 is 1 comma 2. I have an x and y. But there is a big problem here because I don't know dy dt. How am I supposed to find dB dt if I don't even know dy dt? So we're going to have to do a little extra work for this problem. I do have that y is equal to x squared plus 1, which means if I have a relationship between those variables, I would have a relationship between their rates. So dy dt would just be equal to 2x times dx dt. And if I plug in my information, my x is 1, and my dx dt is 2. And that tells me that dy dt is 4. So now I can plug in all my information. 2 times 1 times 2 plus 2 times 2 times 4 over 2 parentheses 1 squared plus 2 squared. Now, my loves, if you just tack on some units, okay, which are centimeters per second, you can leave that answer. If you want to clean it up, that's totally fine. It would give me, let's see, 16 plus 4 is 20 over 2 square root of 5, which gives me 10 over root 5. And if I were to rationalize that, actually, why bother? That's my answer. Okay, so that's just a little bit of a different type of an example, a little bit more abstract, but the same idea. We had centimeters per second. I knew it was a related rates, and I would kind of do it. So you'll have some to practice, and then next class we'll continue on this journey. But that's all I got for you. Have a great day.